Welcome back to more probability. Got two questions I want to go over on the homework, and then we'll move over to the warm-up in today's lesson. So yes, last class we talked about independence and dependence. Two questions I want to go over. The first one I wanted to go over was number 2. A lot of you had the right answer to this, but I'm not sure you had the right work. So let's talk about this for a second. The month of March has 31 days in it. In New York, March has days when it snows, days when it rains, and days when it does both. This breakdown is shown in the Venn diagram below. Based on the diagram, are the events of having snow and having rain independent? Justify. Now, a couple people said that since there was overlap, so they saw that there was 5, there were some days when it snowed and rained, that means it's not independent. So I want to stress, and I'll say this again in the notes today, that overlap doesn't mean anything about independence. It just means that they're not mutually exclusive. And people confuse those sometimes, and I get why. Overlap means they could both happen at the same time, but that doesn't mean one influences the other. If I think of an example, like me oversleeping and there being a thunderstorm tonight would be independent. Me oversleeping this morning has nothing to do with whether or not there's a thunderstorm tonight, but they could both happen at the same time. So that might not be mutually exclusive. It might not be mutually exclusive, but could still be independent. Okay. So if you have data and it asks if something is independent, you need to do a test. And again, I usually gravitate towards the product test. So if I'm trying to tell if snow and rain are independent, I'm going to check is snow and rain, the probability of snow and rain, is that equal to the probability of snow times the probability of rain? Now, again, another thing I saw with this is I saw some people say, okay, well, snow and rain is 5. But that's not totally right, and you'd lose a point for that because it's not how many days have snow and rain, it's the probability that the day has snow and rain. So it's 5 out of the 31 days equals the probability of snow. And again, that's not just 3, that's everything in the snow circle, so that's 8. So that's 8 out of 31 times the probability of rain, which would be 13 out of 31. And I'm checking if that's equal. Okay, so I need to just do 8 out of 31 divided by, or sorry, times 13 out of 31. And I get 0.108, and 5 out of 31 is 0.161. So they are not independent, but not because there's overlap, because that's not equal. And it kind of should make sense if it's not independent, because if it rains on a day, it probably isn't a snow day. Or if it does rain, maybe there's more chance of just precipitation, something like that. But everyone go back and check your homework on this one, because you may have gotten this final conclusion correct, but this is the work you needed to show. The other one I wanted to do was the last question. Carter's team has a hockey game tomorrow. He's a starting goalie for 50% of the games. There's a 40% chance of a snowstorm during the game tomorrow. If the probability that there's a snowstorm given that Carter is the starting goalie is 40%, the two events are, okay, now look at given that. Let's see what we actually have. Sometimes it helps to write everything in probability notation. He's a starting goalie for 50% of the games. So probability starting goalie is 0.50. There's a 40% chance of a snowstorm. So probability snow is 0.40. If the probability there's a snowstorm given that Carter's the starting goalie is 40%, that's the probability of snow given starting goalie is 40%. A lot of people had and here, so be careful of what you do. Based off the information I have, it'd be easier to use the given definition. So is the probability of snow given starting goalie, is that equal to probability of snow? that would mean it's independent, because that means the fact that he was a starting goalie had no impact on the probability of whether or not it snowed. And 0.40 is equal to 0.40. So that means, yes, it is independent. If you wanted to use the product test, you could still do that, but it would be a lot more work because you'd have to use the given formula first, solve for the probability of snow and goalie, and then use the product test. So based off of the information that was given, that was the easier test to use. Okay, hopefully that clears those up. I want to do some practice with two-way tables. So you should have gotten a blank copy of this. If you do, pause the video and go through and fill these out. That's the table I want to do. You might want to copy that down. Then I want to do all of these probabilities plus these ones. Okay, so it might take a few minutes, but see if this two-way table works. You always want to fill out the totals first. When you're ready to see me go on with it, press play. Ready? Okay, we want all probabilities as fractions in simplest form. Keep that in mind. Okay, so I'm going to do these totals. So we've got sophomores, juniors, seniors, and whether they're considered tall or short. So there's 24 here. Oops. There's 13 here. There's 20 here. If I add across, I've got 12 and 13. That's 25. Here, this is 20 and 12. That's 32. So it looks like I should add up to 57. Double check. That's 44 and 13. Yep, all good. So probability or sophomore. Remember, when you see probability of, don't just say 24. It's 24 out of 57. And it wants it as a fraction in simplest form. So I would guess that a 3 goes into both of these. I think, pretty sure 57 divided by 3 is a nice number. That's 8 out of 19. Probability they're short. Total of the short column is 32 out of 57. Not sure if that one's going to reduce at all. Nope. That's that. Probability that you're tall and a junior. Now in the notes today, we're going to be talking about and probabilities more, but from a table, you can just look at where tall and junior intersect. So that's 4. And I'm pretty sure 4 out of 57 can't reduce. Short and a senior. So find where short and senior intersect. There's 12 out of 57. That one should reduce because a 3 would go into both of them. 4/19. Okay, so those ones are pretty easy. Junior, what's this mean? Or you could either use the formula for this, or you could count smartly in the table. We could do probability of junior plus probability of short minus probability of junior and short. Or you could look at the junior column and the short row and just make sure you're not double counting that 9. So first, using the formula, probability of junior is 13 out of 57 plus probability of short is 32 out of 57 minus the probability of junior and short is 9 out of 57. So if you add these two together, you have 45 out of 57, and 45 out of 9 would be 36 out of 57, which should reduce. 12/19. Again, I said you could have also just kept good track of what you're counting. 4 plus 9 plus 11 plus 12. Don't count anything twice. So if I just did 4 plus 9 plus 11 plus 12 out of 57, you would have had 13 plus 13, which is not the same thing. Hang on. Did I do something wrong? Let's double check. 45 minus 9, okay. 13. Oh, what am I doing? 13 plus 23 is 36 out of 57. Yep. There you go. So by the same token, senior or tall, you could use the formula or you could just count. So using the formula, you'd have probability of senior plus probability of tall minus the probability of senior and tall. Probability of senior is 20 out of 57. Probability of tall is 25 out of 57. Minus the probability of senior and tall at the same time is 8 out of 57, because remember we can't count that twice. So this would be 45, and 45 minus 8 would be 37 out of 57. Or you could just count how many seniors, 20, plus how many more talls. So that's 20 plus 17, 37 out of 57. Okay? How about the given probabilities? Now I could use the formula, so junior and short divided by probability of short, but remember you can also count smartly. The first one I'll do both ways, but then after that I'm going to do it the easier way. So junior and short over the probability of short. Junior and short is 9 out of 57. Probability of short was 32 out of 57. But when you multiply top and bottom by the LCD, you'd get 9 out of 32. Now you could also get that by saying, okay, given short, I mean I'm only looking at the short row. Let me erase this that I had before. So out of the 32 in the short row, how many are also juniors? 9. So you could have gotten 9 out of 32 right away. Let's do that because that's a little bit quicker. Short given junior. So out of the juniors, out of the 13, how many are short? 9. So 9 out of 13. Senior given short. So now it's out of the short people. So out of the 32 short people, probability of your senior is 12. So that's 12 out of 32. And that should reduce because the 4 goes into both of them. It'd be 3 out of 8. And finally, short given senior. So out of the seniors, out of those 20, probability you're short is 12. 12 out of 20. Again, a 4 goes into both of those, so 3 out of 5. Okay, so if you're smart with the table, you can avoid the formulas and save a little bit of work. Finally, which is more likely? The probability that person picked at random will be short, given that they're a senior. So probability of short given senior, or the person will be a senior given that they're short. Probability is senior given short. So remember, given probabilities aren't commutative. So short given senior was 3/5. We just did that. Senior given short was 3/8. Which one's more likely? Sometimes it helps to compare the decimals. 3/8 is 0.375. 3/6 is 0.6. So short given senior is more likely. Okay, so I know that was a little bit longer than some warm-ups, but I want to get practice with those two-way tables because that helps quite a bit in probabilities. All right, the last major rule we got to talk about is the multiplication rule. And some of you have already been using this without even knowing it. But let's first go back and review the addition rule. That or probability, probability of A or B, was all about the addition rule. So that said that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And the big thing to remember with OR probabilities is that OR does mean add, but we have to remember to subtract the overlap. We don't want to add certain scenarios more than once. If A and B are mutually exclusive, and we just talked about this again when we went over the homework, mutually exclusive, remember, just means that events A and B have no overlap. So if there's no overlap, what's the probability of A and B? Well, if they can't occur together, probability of A and B would be 0 because there's no overlap. Okay, don't confuse mutually exclusive with independent. Now we're going to discuss the multiplication rule. So now when you've got an intersection, we're looking for the AND probabilities. And we've done these with Venn diagrams and two-way tables, but not with word problems where making one of those isn't possible. The product test for independence gives us a little bit of that formula. We said yesterday, if A and B are independent, then the probability of A and B both occurring at the same time would be equal to probability of A times probability of B. And I put a question mark above that yesterday because we were using that to check if they were independent. So now, if I know that two things are independent, we can find this AND probability just by multiplying them together. So a lot of people think that AND means multiply in probability, and it does if they're independent. What if they're not independent? Well, a couple days ago, we did the conditional probability formulas also. That was the probability of A given B is equal to the probability of A and B divided by the probability of B. Or if it was written in the other way, probability of B given A was the probability of A and B over the probability of A. Now, these formulas didn't rely on A and B being independent whatsoever. And they also have the AND probability as part of them. So I could cross multiply and rearrange, solve for that AND probability, and get another formula for AND. If I cross multiply here, I get that the probability of A and B equals the probability of B times the probability of A given B. And by the same token, I get over here, the probability of A and B equals the probability of A times the probability of B given A. Now note, this kind of ties in with what we just set up here also. If A and B are independent, probability of B given A is just the same as the probability of what? B. So then I have the formula I had a second ago, probability of A times probability of B. So this kind of brings us down to the multiplication rule for probability. If A and B are independent, you're going to take the probability of A and B and say that's just probability of A times probability of B. So you're just going to multiply the two probabilities together. If they're not independent, you're still going to multiply probabilities together, but you're going to take the probability of A times the probability of B given that A already happened. So rather than memorize these formulas, just think about these are going to be multiplied. You're going to multiply the two scenarios together, but if they're not independent, you need to know that the second thing you multiply should be the probability that B occurs given that A already happened. Now, practically, you're not going to really memorize this formula. You might memorize this one. You're going to know to multiply with AND. I'm going to show you that you're going to use this without really thinking about it later. Before we flip to the next page, I want to make one final note. I know I've said it a couple times today already, but it needs to be in your notes somewhere. Note, independent is not the same as mutually exclusive. Mutually exclusive means two things can't happen at the same time. Me oversleeping and there being a thunderstorm later in the night are not mutually exclusive. They could happen at the same time. Independent means one doesn't affect the other. Me oversleeping and there being a thunderstorm this evening would be independent. They don't affect each other. Okay, let's get to some examples. We'll start back with the spinner again. Same spinner you've seen on a bunch of note days. If we spin it more than once, are the outcomes independent or dependent? So if I spin this one time, look where it lands. Spin it again, look where it lands. Is that independent or dependent? Hopefully you're all thinking independent. And to explain it, no spin relies on the outcome of the previous spin. So if it's independent and I have an and probability, now I know I can just multiply probabilities. Okay, I don't have to worry about what happened on the previous outcome. So what's the probability of spinning an even and a 7? The probability of even and 7 is just probability of even times probability of 7. And the probability you get an even would be 4 out of 8, or 1/2. Probability you get a 7 is 1 out of the 8. When you multiply those, you get 1/16. Remember, multiplying fractions, just multiply across the top, multiply across the bottom. What's the probability of spinning a 7 and then spinning an even? Probability of 7 and even would be the probability of 7 times probability of even. Well, it should be no surprise that 1/8 times 1/2 is still 1/16. Since multiplication is commutative, so is this. What is the probability in 2 spins you get a 7 and an even? Now this is slightly different. There's 2 scenarios this could be. This could be the probability that you got an even and then a 7, or you got the probability of a 7 and then an even. Now the wording is really tricky in probability. These two were very specific. You spun an even and then a 7, one scenario. You spun a 7 and then an even, one scenario. But this just says in 2 spins, one of them's a 7 and one of them's an even. It doesn't specify the order. So you need to take both possibilities into account. You know both of these probabilities are 1/16. What do you think I'm going to do with them? Well, if this one can happen or this one can happen, we're adding them. And there's obviously no overlap here. You can't be this scenario and this scenario at the same time, so that's why I'm not subtracting off the overlap. When you're adding fractions, you add the numerators and keep the denominator the same. So this ends up being a probability of 1/8. It's a better chance that you get a 7 and an even over your 2 spins than you have specifics. Okay, number 2. Suppose a power generating facility has 3 primary safety switches in case of an emergency. The probability that any one of these switches fails is 5%. What's the probability all 3 will fail given the switches are independent? They told you independent. As soon as you see that, you can just multiply without worry. So I would say the probability that the first one fails and the second one fails, and the third one fails. You can multiply all three. I know the formula we just did had two things multiplied, but you can extend it to multiply as many scenarios as you need. So it's going to be 0.05, 5%, times 0.05 times 0.05. The probability of any individual one failing was 0.05, and they were independent of each other. So I could just do 0.05 cubed. And it comes out to be a crazy looking number. Remember, that's move the decimal place 4 to the left. So 1, 2, 3, 4 would be 3 zeros. So that's going to be 0.000125. And if I want it as a percent, which is like how the probability started, I move that decimal place back 2 to the right. So 0.0125%. So pretty low probability that all three safety switches would fail at the same time. Okay, last one on this page. Suppose that a credit card company states that when a customer is selected at random, the probability that the customer pays his or her bill in full each month is 35%. The probability that the customer makes regular online purchases is 83%, 0.83. These two events are independent, so I can just multiply. Let's write what we know. Probability pay in full is 0.35. Probability it makes online purchases, so probability of online, is 0.83. And whenever you have word problem probability questions, I would suggest writing those out. Write out in probability notation what you know. Okay, what's the probability that a randomly selected customer pays his or her bill in full each month and makes regular online purchases? So this is probability that you're paying in full and making online purchases. Since they told me it was independent, what am I allowed to do? Just multiply them. So it's be the probability of pay times the probability of online. So it's 0.35 times 0.83. And if I do 0.35 times 0.83, I get 0.2905. Okay. Now part B, what's the probability that a randomly selected customer pays his or her bill in full each month or makes regular online purchases? So now I'm going back to probability of pay or online. So I like this question because it brings an old formula into it. This is where I do probability of pay plus probability of online minus the probability of pay and online. Well, the probability that we pay in full we know is 0.35 plus the probability we make online purchases, we know that's plus 0.83 minus the probability that we are paying and online. We just found that in part A, 0.2905. So 0.35 plus 0.83 minus 0.2905, 0.8895. Now, as a follow-up question to that, is paying in full and paying online mutually exclusive? No, it is not, because there is an overlap. This probability in part A wasn't zero. So again, you can be independent and not be mutually exclusive. They're not the same thing. So let's make a note. Not mutually exclusive. Because probability of A and B is not zero. Okay, so everything we've done so far has been independent. Let's look at what, if it's not independent, what it looks like. Certain Algebra 2 class consists of 13 girls and 11 boys. 3 lucky students will be randomly selected to go on a math field trip to spend the day with a New York Yankees statistician. Wow. What is the probability that only girls are picked? Before we answer this question, let's think. What are the 3 events that are going to happen? Okay, so event 1 is there's a girl picked first. Event 2, there's a girl picked second. And event 3, there's a girl picked third. So 3 events have to happen all at the same time. We want the probability that only girls are picked. So essentially, in terms of these events, I want the probability that a girl is picked first, and a girl is picked second, and a girl is picked third. Are these events independent? Does the fact that I pick a girl first affect the probability of picking a girl second? And here the answer is yes, it does affect it. So they're not independent. Because if you pick a girl first, there's one less girl in your class and also one less total number of people in class. It's kind of like that with replacement, without replacement thing. The same girl can't get picked all 3 times. So the fact that the girl is picked on the first one is going to affect how many girls are left to pick on the second one. So who is picked first influences probabilities of who is picked, who could be picked second. And you want to think of this as the scenario that we've talked about before, I think in the last class, without replacement. Whenever I'm not replacing something in my pool of possibilities, then I'm not independent. So the way I'd use the multiplication rule this time, I'd still do the probability that girl 1 is picked, the probability that girl 2 is picked, times the probability of girl 3 is picked. The probability the first person picked as a girl is 13 out of 24. But now the second one isn't 13 out of 24 again. There's one less girl and there's one less student. So now it's 12 out of 23. And the last one is, right, 11 out of 22. So when I multiply those together, this isn't as easy to do without a calculator, so let's pull it out. 13 out of 24 times 12 out of 23 times 11 out of 22. When I math bracket, I get 13 out of 92. Now, I told you at the beginning of class today that you would use the second case formula without really thinking about it, and that's what we just did. If I flip back to the front real quick, we just did this formula. The probability that a girl was picked, and then the probability that another girl was picked, given that we already knew the first girl was picked. This was the probability that a girl is picked. This is the probability that another girl is picked, given that we already knew this first person was a girl. So that was using that second formula, but you still just think of it as the multiplication rule. You're just smart about what your probabilities are. Okay, last question on this page. How can we determine the probability of at least one boy being selected? Well, at least one boy, think of this, there's a lot of possibilities. It could be boy, girl, girl, boy, 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 that's still at least one boy, girl, girl, boy, there's lots of possibilities. Sometimes it's easier to think what is not included here. So at least one boy would be every scenario except all girls. So if I want everything except all girls, which I just found up here, what's the easiest way to do that? 1 minus the probability. First is a girl, second is a girl, and third is a girl. Remember that complement idea. So it's 1 minus 13 out of 92, which would end up being 79 out of 92. So if something seems really tricky, think if you could make it into a complement. All right, last page. A bag of marbles contains 12 red, 8 blue, and 5 green. If 3 marbles are pulled out, find each of the following probabilities. In each, we're going to specify either with replacement, meaning you take a marble out and you put it right back, or without replacement. Find the probability of pulling 3 green marbles with replacement. So with replacement, again, that means it's independent. So probability of green and green and green. We just got to multiply the probability of green 3 times. So that's 5 out of, how many total marbles have we got here? 20 plus 5, so it's 25 total. So 5 out of 25 times 5 out of 25 times 5 out of 25. Easiest way to type that into your calculator is just 5 out of 25 cubed, and you get 0.008, which is the same as 1 over 125. Now I want 3 red marbles, but without replacement. That means it's not independent. So the only thing you have to worry about is you have to be more careful about your probabilities. The first one being red would be 5 out of 25, but the second one being red would be what? 4 out of 24. And the last one being red, 3 out of 23. Oops, shouldn't be equals there. So do that. 5 out of 25 times 4 out of 24 times 3 out of 23 gets us to, math bracket, 1 out of 230. Now, I just realized I looked too close. I did the green ones again. So let's just change this to saying green, and then we don't have to redo the whole question. Sorry about that, but you get the idea. And the probability of pulling out 3 marbles of the same color without replacement. So again, not independent. This one's a little trickier. This would be the probability of red, 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 or the probability of blue, 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 or the probability of green, green, green. So I have to find all of these and then add them together. And it's without replacement. So red, red, red is going to start as 12 out of 25, but then it's going to be 11 out of 24 and 10 out of 23. Or I'm going to add blue, blue, blue would start at 8 out of 25. Then if I'm not replacing, then it's 7 out of 24 and 6 out of 23. Or finally, green, green, green is one we just did. 5 out of 25 times 4 out of 24 times 3 out of 23. Now we know this last one is 1 out of 230 from the last one. And I could type these into my calculator, but just to speed things up for you a little bit, this comes out to be 14 over 575, and this one is 11 out of 115. So when I add those three fractions together, this plus this plus this, I get my final probability of 14 out of 1150. Okay, and then finally the last one, find the probability of pulling out 2 blue marbles and 1 green marble in any order with replacement. So now I'm back to being independent again. So 2 blue and 1 green in any order. I have to do the probability of blue, blue, green, or the probability of blue, green, blue, or the probability of green, blue, blue. And since it's with replacement, this is going to be 8 out of 25. There's 8 blues times 8 out of 25 still, because I'm replacing it back in, so the probabilities aren't affected. And the green would be 5 out of 25. And if you notice, all these are going to be the same, just in a different order. This is 8 out of 25 times 5 out of 25 times 8 out of 25. Same thing, because multiplication is commutative. And this is 5 out of 25 times 8 out of 25 times 8 out of 25. So all three scenarios are going to come out to the same thing, 64 out of 3125. But since any three of these scenarios is legitimate, because it doesn't specify the order I have to pull them out, I have to consider all three, add them up. My answer is going to be 192 out of 3125. All right, so sorry that was a little bit long, especially with the warm-up, but I hope you understand how to do ANDs probabilities. Good luck with the homework and email with questions.